Welcome to the introduction of sequences and summation. This is about leading into arithmetic and geometric sequences and series. We are going to be going over sequence and summation notation and how it will apply to sequences. We will be discussing recursive formulas, factorial notation, and properties of summation notation. Let's consider the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, and so on. This sequence was investigated by Leonardo of Pisa. He was an Italian mathematician who studied rabbits and their procreation and their pairing when starting out with an initial set of one pair. One thing that's really important in this sequence is the order and the placement of numbers. Each of these values or terms, 1, 1, 2, 3, 5, is set up in a sequence that cannot be altered in their placement, and we like to call that placement n. So the first term is 1, the second term is 1, the third term is 2, the fourth term is 3, and so on. So n is very important. We can think about the Fibonacci sequence as a function, and we'll go ahead and define that function here shortly. The domain is the set of positive real numbers. We are calling our domain n, what goes in our function. And the terms a sub 1, a sub 2, a sub 3, or our 1, 1, 2, 3, 5, those terms are the values that are represented here. When n is the whole set of positive numbers, it is called an infinite sequence. So n goes on forever to infinity. And sequences whose domains consist of the first n positive numbers are called finite. We can define the Fibonacci sequence by looking at the first two starting points. So the first terms are 1 and 1. There really isn't a big jump or a pattern involved here besides that they are the same. It is when we see beyond that, let's say f of 3, that we could see the value of 2 is equal to 1 plus 1, or the previous term plus the term prior to that. So we can define the Fibonacci sequence f of n as f of n minus 2 plus f of n minus 1. We are building upon the previous two terms to get the next value, and this is an example of a recursive formula. We won't be going too much into the Fibonacci sequence right now, but it is a very important sequence in nature. We can see it in acorns and pine cones and shells, and it's a very beautiful thing, and even plants. Let's go ahead and let's find the terms of a sequence from a general term. That means we can write the terms of a sequence by evaluating the general term, or what we're going to be called a general function. You can think about it as a general function, defining what is happening to a sub n in this expression that we are going to plug in our domain to generate the terms of the sequence. Okay, in example 1, we are asked to write the first four terms of a sequence given a sub n equals 3n plus 4. What we're going to do is we are going to set it up so every single time we see an n, we are trying to substitute whatever placement we're looking for. So I'm looking for the first term, so wherever I see an n, I'm putting a 1, so I have 3 times 1 plus 4, which is equal to 7. I'll go ahead and write my sequence also over here. A sub 2, wherever I see an n, I have 3 times 2 plus 4, so my next value is 10. A sub 3, again, easy as pie. Wherever I see an n, I put a 3, and I go ahead and have 13 as my next number. We're basically adding 3 to each of these values, and it started at 4. We'll be going over arithmetic sequence definitions and its patterns in the next video. For a sub 4, we have 3 times 4 plus 4, that's a 4, and that's 16. So we have just written the first 4 terms of the sequence by inputting and changing the n. Again, let's go over a different sequence here, and this may scare you a little bit, but when you see that negative 1 raised to a power, it's nice because you're really going to want to remember this. This is alternating the sign. So negative 1 So the first power is simply -1. -2 squared, negative and negative is a positive. That output becomes positive. And -1 to the third is -1 also. So we are going to recognize a sign change here at every single one of these terms. If we go ahead and plug 1 in for n, wherever I see an n, I have -1 to the 1 over 3 to the 1 minus 1. And if I do the math, my first term is -1/2. You go ahead and write my value here. I know I'm going to be finding 4 terms, so I'm going to set that up. A sub 2, if I go ahead and plug in 2 wherever I see an n and do the math, I end up with 1 over 8. So I have 1/8. And you see that that's negative and it turned to positive. Let's go ahead and evaluate a sub 3, plugging in a 3 wherever I have an n. And doing the math, I have -1/26. Okay, you can see the denominator is getting bigger and bigger due to the 3 to the n. So we know that a sub 4 is going to have an increasingly larger denominator and also have a positive value as we evaluate -1 to the 4th. And indeed, we have 1 over 80 as our 4th term in this sequence. So we have just generated the first 4 terms given this formula. I would like for you to complete the Got It questions number 3 and 4 using the same plug and play type of math. And if you have any questions, go ahead and ask your teacher tomorrow. Let's go ahead and move on. Once you are done, you can pause the video to work on the Got It questions. But let's go ahead and move on and define a recursive formula. Now, the Fibonacci sequence was a good example of a function that defines the nth term of sequence from the previous term. And there was always a starting point. There is always a starting point in a recursive formula because we have to be building on a previous term. We can't just build off of nothing. So we are given a sequence where a sub 1, or the first term, is 7, and a sub n is defined by 5 times the previous term plus 2 for any n greater than or equal to 2. So if we go ahead and we want to find the next term, a sub 2, I can define a sub 2 as 5 times a sub 1 plus 2, and we just were given the first value, so I have 5 times 7 plus 2, and that equals 14. So our first term is 14. We can go ahead and keep on building off of our previous term. So a sub 3 is 5 times a sub 2 plus 2, and we just calculated that out. So 5 times 14 plus 2 is 72. This is getting big quite fast, so our next term is 72. Then we have a sub 4, our last term, and I have 5 times 72 plus 2, and that equals, let me do the math here, 360. Now I have actually forgot here to list my first term. So the first 4 terms are 7, 14, 72, and 360. Again, going over another example, in example 6, we have an initial starting point of a sub 1 equals 4, and we're asked to find the first 4 terms of a sub n equals 2 times the previous term plus 5. So let's go ahead and calculate that out. A sub 2 is defined as 2 times the previous term, so a sub 1 plus 5. And we are given a sub 1, which is nice, so we have 2 times 4 plus 5. And we have 13. So I like to write my terms out here on the right so I remember what I am calculating here. And a sub 3, that equals 2 times a sub 2 plus 5. And we figured out what a sub 2 is, so I have 2 times 13 plus 5. So a sub 3 ends up being 31. going to fill in my 31 right there. And a sub 4 is 2 times 31 plus 5. And doing the math, I end up with 67. Now with recursive formulas, it is very nice to actually work vertically up and down. These notes are kind of cramped, so if you want to use your space on another piece of paper, that is perfectly fine. That may be helpful when you calculate the Got It question example number 7 and 8 using and modeling what I've just calculated out for you. So please pause the video and go ahead and work on those. The next thing we're going to do is we are going to find terms of a sequence using factorial notation. And this should be somewhat of a review. You should have seen n factorial before. When we see that n exclamation point, it doesn't mean that it's just a happy n. It really just means, and it reads n factorial. Although I find this a very happy subject, I really do indeed like looking at exclamation points. This is the product of all the positive integers from n down to 1. So when you see n factorial, you have n times the number below it, n minus 1, times the number below that, n minus 2, all the way down to 1. We have a special definition for 0, where 0 factorial equals 1. What's going to be helpful for you is, let's just go ahead and maybe you should memorize the first or so terms of factorial. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2, which is 6, 4 factorial is 4 times 3 times 2, and that equals 24, 5 factorial, so 5 times 4 times 3 times 2, that equals to 120, and we are getting significantly larger every single term increase. 6 factorial is equal to 720. And 7 factorial is a whooping 5,040. I would like for you to memorize these, recognize these values, because they will be sneaking into your evaluation of series and sequences, both in arithmetic and geometric. So let's get some practice with evaluating factorials. I have 11 factorial over 3 factorial times 6 factorial. By definition, I can actually pull out some numbers from 11 factorial. If 11 factorial really means 11 times 10 times 9 times 8, I can go ahead and keep on extracting that until I get down to 6 factorial. I chose to stop at 6 factorial because I would like to cancel out 6 factorial because I have it in my denominator. So here I've just canceled both of those values out. And if I calculate this and punch that out on my calculator, it equals to 9,240. You can easily find your factorial notation button on your calculator. I know it's built in, and even I think a shortcut on your TI-84, and it's kind of a little more hidden on your 89. So there is a TI-89 and 84 tutorial that is on the website for you to view if you would like to take a look at how sequences and factorial applies to your calculator. Let's go ahead and evaluate a more general relationship of factorial. I have n minus 1 factorial over n factorial. And I'm choosing to ignore the numerator at this moment because I can play around with n factorial. I can extract that n out because n factorial is just n times n minus 1 times n minus 2. And I choose to do that because I can easily cancel out the numerator with that n minus 1 factorial on the bottom there. And if I were to simplify, this really equates to 1 over n, a much more simpler way to represent this. I'd like for you to complete the Got It example number 11, so go ahead and pause the video and we'll go on.